I did say what I think I wanted to say about general relativity in the last video, however, it was really quite near the end of the last video. So I think I'll begin again by saying that I don't think that general relativity makes the right assumptions in equating, for instance, energy with momentum or these ideas of length contraction. I think they're sort of wrong. I don't think that they necessarily point in such bad directions mathematically, and I'm sure you can massage the mathematics to basically say whatever you want to say or make what you want come out of the equations one way or another. However, I think, for instance, when you get a photon approaching a black hole, it's going through this firewall for one thing, this area where it's accreting all this gas, dust, rock, etc., and it's accreting that gas, dust, and rock for some reason that I'll come to in due course. But the photon, like rather than the length scales itself being contracted down or compactified into a smaller area, as general relativity would have it, instead of that happening, what's really going on is it's entering the black hole, it's bouncing around between all these particles of gas, dust, rock, and so on, and also what I imagine are background electrons keeping that gas, dust, and rock there in this sort of firewall where you have this huge amount of trapped energy, of trapped photons, right, surrounding the black hole's event horizon. But yeah, so length contraction, that doesn't really happen at all, or it doesn't really happen in quite the same way that people think it does. And it has nothing to do with this sort of trampoline-like substance of space-time in the background that stretches and squeezes. That's how it appears to be, I grant you, but that's not the way that it really is, I don't think. And I think that on a very deep and important level conceptually, general relativity is in fact wrong and invokes the wrong assumptions. And we get into all these notions of Minkowski spaces and anti-de Sitter spaces and de Sitter spaces and all these sorts of curved spaces and these Riemannian geometries. It's all very mathematically beautiful, I grant you that, but I think this is one of the major problems. And general relativity is a sort of sacred cow in physics that you can't really attack. Right, it's one of these grand, beautiful theories, very well evidenced, very well established in evidence, that you can't really attack on this sort of fundamental level, where it might be giving us really the wrong sort of concepts to work with. But nonetheless, I think that if we want quantum gravity, what we have to really start invoking is, of course, quantum concepts. So you want gravitational fields to be made of quanta. Okay, so you obviously want some sort of particle to be mediating the force of gravity. So what's the first and most logical thing to do? Well, I think it's probably to fish around in the agglomeration of particles that we have at the moment, i.e. the standard model of particle physics, to see if any of those particles sort of make sense to be mediating the force of gravity. So, like, one candidate does pop out as being particularly favourable, I think, and that's the electron for a particle of gravity. Mostly because it interacts with particles of light. So when you get this gravitational lensing effect, for instance, around galaxies. You get these sort of Einstein rings, whereby you have the light being lensed around galaxies. What that would really be is that around especially dense galaxies, you have an electron density, light goes in, bounces around inside the electron density, gets trapped there, and then gets emitted again out towards our telescopes such that we can detect it. And again, it's not the space-time curving around it. What it really is, it's a particularly dense agglomeration of electrons in the background, tunneling all the time, just like they do sort of around atoms and molecules and things. And then we find at the extremities of such galaxies that they emit photons, and in certain configurations of galaxies, and when they're particularly dense and so on, we find that they exhibit something a bit like an atomic structure, and you have sort of the nucleus of the galaxy at the center, and the extremities of their electron density at the extremities of the galaxy, and they do sort of behave a bit like well, not atoms as such, since atoms don't quite curve the light around them, they do reflect the light off of them, but they do, for this reason, create a sort of a lensing effect from their electron densities, from their gravitational fields. So the electron is a particularly favourable candidate for a gravity particle, since it's charged, so if it tunnels into the electroweak range of another atomic nucleus, it can exert a force of attraction over that nucleus. It also resists, so we might be able to explain things like the perihelion precession of Mercury this way, because Mercury is a non-rotating body, So the electrons surrounding Mercury won't be impacting constantly the electrons in its background, which is the electrons from the sun. And we see the corollary of this in Earth's rotation. Earth doesn't precess on its orbit, so there's not much precession in Earth's orbit compared to Mercury's. The Moon is also tidally locked, and that has quite a lot of precession in its orbit. It has precession in its orbit quite often, about 100 years or so, kind of like Mercury does, or 60 or 70 years or so, or something like that. And yeah, there's all sorts of good reasons for thinking the electron is a very important particle in gravity. Then there's things like Hawking radiation. If an electron can tunnel within a black hole's event horizon, absorb a photon, jump out again to some different part of the universe, emit the photon, then that explains information loss of black holes, does it not? Since photons are obviously information, photons do have mass associated with them, or they have mass energy associated with them, and you can get these explanations of quantum phenomena on a macroscopic scale via invoking this central sort of assumption. But when it comes to length contraction, this idea of conflating our units of or our fundamental constants associated with the force of gravity and the speed of light, I think that leads down a deep rabbit hole of dimensionlessness, or nth dimensional thinking, or infinite numbers of dimensions, or like 6 or 7 or 12 or 11 dimensional space. And this is where all this string theory stuff comes from. This is where these extra dimensions to reality comes from. It comes from this compactification down of space, the contraction of length surrounding black holes. And I really, really don't think that that's quite what's happening. What I think more like is what's happening is that light is slowing down. That's in essence what's happening at a classical level. And maybe on a level you can say also that the lengths are being contracted, but I'm not so certain about that. Not from a classical physics standpoint anyway, or not even from a quantum perspective, really. Not in a background dependent quantum theory. I'm not 100% convinced that lengths themselves are contracting. I'm sorry to say. I think what's really going on, is that light on a classical level, or on a quantum classical level, should we say, is being slowed down by the presence of very large masses. And general relativity is motherfucking wrong. And we've got to accept that. And there's huge holes in general relativity anyway. Like the dark matter problem, which can be solved by invoking electron densities. The dark energy problem, which likewise can be solved by invoking electron densities as gravitational fields. And all this sort of stuff that I've elaborated on for many years, but no one's fucking listened to. Oh well. And, singularities, well, those exist. Singularities are, well, why am I talking about singularities now? I don't really know why. What was I going to say about singularities? I was going to say every time that an electron impacts with a photon, every time an electron impacts with a photon, the electron collapses into a singularity and disappears to somewhere else in the universe, deposits a photon somewhere else in the universe, an electron pops up to take its place, which we know is probably happening due to non-local realism and the violation of Bell's inequalities. And this entanglement stuff is going on, but entanglement isn't really what we think it is either. It's entangled tunneling, whereby two electrons have more or less the same energy state, and they tunnel between one another's locations in experimental settings and deposit a photon into the experiment, trap the photon again, tunnel to another location, another electron pops up with a different spin. C'est la vie. That actually led me to think that electrons might be monopoles. At a very, very fundamental level, I think they might be monopoles. They might be magnetic monopoles. And this is because they would average out to a dipole, but each time the electron appears, there's a different electron from somewhere else in the universe. So it might be roughly spin up or spin down. It might be sort of orthogonal-ish to the electron that departed. It might have the opposite spin, or it might have the same spin, but it appears and disappears so many different times, with an electron of a different orientation in space, as a monopole. but emits the photon. This is just going into speculation, right? But emits the photon at a different angle, and averaged out over many appearances and disappearances of many different electrons, which we perceive to be the same electron, the same free electron, or the same atomically bound electron. It certainly looks like a dipole, or is a dipole from that temporal frame of reference. But yeah, I mean, getting back to general relativity, yeah, I think it's wrong. I think it's flawed on all sorts of levels, or on a few levels. What it's comparable to really is Newton's theory of gravity, which, I mean, is an excellent theory of gravity. It's 99.97% the right answer. Well, no, it's 97% the right answer. General relativity is like 99% the right answer. My theory of gravity is like 99.7% the right answer. I'm sure it's not everything to do with gravity. I'm sure there's more mysterious stuff playing, but I mean, maybe I've contributed that 0.7 to gravity. That'd be a fine accolade, I think. If I contributed that sort of thing to gravity, I would receive a Nobel Prize. But then again, really, it's not my work, obviously. It's Felix Finster's work, it's various other people's work. Maybe I've contributed a little bit to that work, and what I've done deserves to get published, because it's a contribution to causal fermion systems, and that sort of understanding of it, but it bisects with, or intersects with loop quantum gravity and Euclidean quantum gravity, and to some extent string theory, I think, since loop quantum gravity and string theory don't cancel one another out, and all these mathematical models, in the mathematical sense, they are sort of right, and they do sort of have something to say about physical reality, but they ain't all correct, and I'm just as correct as they are. But I think my interpretation of it, at least, and maybe I'm just more of a reporter of science, or more of a philosopher of science, gaining a physical interpretation out of things. I think that, yeah, gravitational fields are rotating electron densities if the body to which they're paired rotates. That's the solution to the problem of dark matter, since it creates electrical resistance between two electron densities. Say, for the rotating Earth and the Sun's electron density in the background, causes it to be more stable on its orbit. Likewise applied to galaxies and rotation curves in galaxies. There's fewer electrons at the extremities of galaxies, so there's less resistance there in the background for stars to rotate through. So the rotation curves at the edge of galaxies is quicker for stars at the extremities. Oh, unlucky, I'm going to end this on 13. I've got to stop being so superstitious. Stupid little superstitions, like seeing a number 13, like, I'm going to have bad luck. Oh well, shitty me. Oh well, I'm going to see you soon anyway, and thanks for talking to you, it's always been lovely.